Hi everyone, it's Nathan, and because this is the first one of these that I'm doing, I just wanted to give a little preface for what this is. So obviously the setup's a little bit different than what I would do in a normal talk video, and the point of this is that I'm just basically going to give an academic talk. I want to have a way of documenting academic talks that I give as I go throughout my PhD process, and later on if I give talks elsewhere about different things, I want to be able to document that I've given talks when I'm allowed to on this channel. So in a second here, I'll go ahead and just start giving an academic talk. It'll be a little bit more rigorous and dense than, or at least assume more background knowledge than an average talk video would, where those are more geared towards developing intuition and maybe like a basic development of rigor in a certain subject, or just to better expand my knowledge on a math thing that I am interested in. Whereas this will be pretty much just straight math for the most part. And so it's not going to be edited a ton. It's just going to be me talking a talk. So with that being said, I'm just going to flip it over. Today, I'm going to go ahead and talk about the complexity of two-dimensional symbolic spaces. This was a talk that I gave at the STaRS seminar at the University of North Texas. So the STaRS seminar is the Students Talk Research Seminar there. It's run by a few professors and lecturers, but in particular, Dr. Kawamura invited me to talk about what I did, my senior thesis sort of thing of my undergraduate career on. And so this talk is based on, well, it's a version of the STaRS talk that I gave just a couple weeks ago, but it's also based on the presentation I did as a part of my integrative exercises with Neerja Kulkarni, who is now a PhD student at Caltech, Dan Weathers, who I thought he was going off to do his PhD at some point, but I haven't heard anything. And then it was under the advisement of Dr. Elizabeth Sattler, who is a assistant professor up at Lawrence University in northern Wisconsin now. So with that being said, we're gonna talk about some things. So this talk, it can be broken up into 5 sections, the first half of which is covered by the first 3. So first off, I'm going to go ahead and give some motivation for the things that I want to talk about. Next, I will introduce symbolic dynamics, and I'm going to try to do this in parallel. So because I'm mostly concerned with two-dimensional spaces in this talk, I'm going to try to do the one-dimensional and two-dimensional introductions side by side just to save time. And then third, at the end of the first half of the talk, we're going to talk about what SFTs are, or shifts of finite type are, a way to think about the complexity and thus an intuition for this value called entropy. And then in the second half of the talk, I will go ahead and explain the thing that my group sort of threw at a wall for 6-ish weeks, trying to figure out a way to quantify the complexity in a different way. And at the end, I will go ahead and go through a lot of the questions that we had about this thing that seemed to stick, but we weren't able to prove much about. So with that being said, which is, I guess, a phrase that I use a lot when I talk, let's talk about some motivation. So I want to go ahead and give a few different things that you can think about as I talk through this stuff that hopefully you can go back to if you're not super sure about what does this mean or where does it apply and that sort of thing. So I'm going to start on the theoretical side of things. And in particular, I want to talk about tilings. So two-dimensional symbolic dynamical systems can be expressed and connected to different types of tilings. And it's something that tiling the plane has been, so let's try that again. Tiling the plane has been something that people have thought about for a long time. I mean, talking about tiling the plane with different regular polygons. I have a video on my channel about tiling the plane with pentagons. And then also computer scientists sometimes think about these types of things. In particular, if you wanted to, you could go ahead and do all of your computational complexity development through something called a tiling machine, which is just like a pictographic analog to a Turing machine where you build up a tiling based on the moves that a Turing machine would do. So one of the simplest examples of a tiling is something called a Wong tiling. And so your tile set are going to be these 4 squares, and they'll have 2 different colors. And the rule with a Wong tiling is that there's a color matching rule. So tiles can be laid down next to each other as long as they match colors on the side. So this is an example of a partial tiling of the plane with this tile set of Wong tiles. And the connection to symbols, which I still haven't defined, is going to be that you can sort of take a tiling and you can go ahead and identify each tile or different aspects of those tilings with symbols. So in this case, I went ahead and just identified a tile with U, D, L, or R based on where the orange edge is. So if through this mapping, if you see a U in this array of symbols, then that came from a tile that has an orange colored edge at the top of it. So you could do this with other aspects of the tile. You could, instead of using UL, DR, and just looking at the tiles themselves, you could look at like the edges of the tiles and perhaps have like B for a black edge and O for a orange edge, and then do some mangling of the integer lattice to go ahead and get a similar array that describes the partial tiling on the left, but with 2 symbols instead of 4. The other thing that I want to connect symbolic dynamics to is an application in the real world. So let's talk about data storage for a second. Because biomathematics is like a pretty big and active area of research currently, the first example I'm going to talk about is that of DNA data storage. So this actually comes from a scientific report published by Nature, and it gives you an example of an encoding scheme for a DNA data storage system. So this particular coding scheme comes from a larger diagram that is cited in the caption of the figure below. So if you want to see the full diagram and read a little bit more about how DNA data storage works, I totally encourage you to do so. However, the thing I want to focus on about this is that the cool thing is that you can express data as binary, and through different coding schemes, you can go ahead and turn that binary data into a string of nucleobases of DNA. And I have another video on my channel about DNA data storage as well. So if you want to hear more about that, I will put it up in the cards as well of this talk. So you can go ahead and take binary data that we usually associate with computers, turn it into this string of nucleobases of DNA, and then you can actually go ahead and read it back and decode it and error correct it, which makes DNA a viable data storage system. And the complexity of different symbolic dynamical systems and how you're restricted in the way that you can go back and read that data is often connected to some of the restrictions that I'll talk about later. But this is more so like a one-dimensional case thing. In the two-dimensional case, the more pertinent example is that of holography and holographic data storage. So this is an example of a simple holographic data storage system that was published in the IBM Journal of Research back in 2000. And the important thing that I want you to take away from this image is that you've got this array of lights in this spatial light modulator, and they can either be on, which would be a 1, or off, which would be a 0. And somehow you're using that array of lights to go ahead and store data in an array. And so Lind, who is one of the he's a symbolic dynamicist, or at least he was one of the authors of one of the books that I will cite at the end in my biblio about symbolic dynamics. He mentions that a lot of the finite type restrictions that we will talk about apply to holographic data storage methods. And these are more commonly found in computer systems today. So that's where stuff applies. I should probably start talking about the math stuff that I'm going to talk about. So, what is symbolic dynamics? So let's start bare bones basics. First off, we start with an alphabet, which is a collection of symbols. Take your native language that has an associated alphabet, and that would be a collection of symbols. So it is an alphabet in this sense as well. The other one that's more familiar for data storage is just binary, which is the alphabet of 0 and 1. In one dimension, when we go ahead and take our alphabet, we want to go ahead and start building things with that alphabet. So in one dimension, we look at words, which this A star is going to be the set of all finite words that are formed with symbols in our alphabet. And then in two dimensions, we look at patterns, which I'll just use this fancy P as the set of all finite patterns. So for an example, in binary, a word would be something like 0110, which is a word of length 4, and it lives in the set of all finite words on the binary alphabet A. And then for patterns, we can have any weird array of symbols. For that, the only thing that we'll stipulate is that these patterns need to be somehow aligned on part of the integer lattice. So you can't have like weird overlapping of symbols or things like that. So this first row 0, 1, second row 1, 0, 1 is an example of an element in the finite patterns list for the alphabet A. All right, so for those of you that care about topology, we're going to go ahead and say that A, the alphabet, is a set endowed with the discrete topology, which is important in the background of what's happening, but I won't talk much about topology. I'll talk about it enough to just introduce the types of topologies that are on these things. So next, we have our finite words, and we want to go ahead and start building infinite things, sort of like the tilings were at the beginning. So what we do is we go ahead and look at this A to the Z thing, which I'll define here in a second, but algebraists and analysts often think about this A to the Z thing as a function space. We're not going to do that, though. And in the two-dimensional case, we have a similar notation of this A to the Z squared, which is just A to the integer lattice. And again, that can be thought of as a function space, but we're not going to do that. In particular, we're going to think about this is a bi-infinite string of symbols. So if our alphabet is binary, an example of one of those bi-infinite binary strings that lives in this A to the Z thing is shown on screen right now. And then in the, and we often refer to these types of points as addresses. And so Barnsley, who's a famous fractal geometer, he often looks at like one-sided versions of these points and uses those and calls them addresses to identify points in a fractal construction. Whereas in the two-dimensional case, we'll look at these infinite arrays of symbols, like we saw with the tiling example earlier on. So this is an example of a binary, a point in this space given by, not given by, but where the space is generated with the binary alphabet. And to give it like a geometric feel, again, I'm going to lean back on tilings, so we can go ahead and identify each symbol with some element, some characteristic of a tile or a tile themselves. So in this case, I just went ahead and connected the zeros to blue squares and the ones to orange squares, and we could generate a tiling just based on the instructions that are observable based on what symbol is where. And there are several different ways that you could do this, right? You don't just have to make things blue squares and orange squares. You can do all sorts of constructions if you want to. The topology on these spaces of symbolic points is going to be the product topology. So you just take the product of all of these discrete topological spaces and you get the product topology for these infinite string and infinite array, or bi-infinite string and directionally infinite array spaces. So let's talk about dynamics. Well, sort of. We're gonna loosely talk about dynamics. So next, I need to define what the shift map is. So the shift map is what generates some dynamics on these spaces. So in one dimension, the shift map sigma acts on a bi-infinite string by just shifting everything over by one index. This is why I've been putting decimal points in the middle of these bi-infinite points and in those directionally infinite arrays, is because I want to be able to visualize what happens. So if we have a point in the a to the z thing for the alphabet of binary of just 0, 1, we can look at the bi-infinite string that's just all zeros to the left and all ones to the right, and when we apply the shift map to it, it's going to move that center or that decimal point over to the right by 1. So instead of having all zeros to the left of it and all ones to the right of it, we're going to have all zeros and then a 1 to the left, and then we're going to have all ones after that. A shift space then is some subset of that a to the z thing, which is a collection of bi-infinite strings that has the following properties. One, it's going to be shift invariant, which means that for every point in your space, the shift of that point is going to live in the space as well. And secondly, if your space is closed with respect to the product topology, it's not if the space is closed with respect to the product topology, it's that the space is closed with respect to the product topology, which again, I mention it because it's part of the definition, but it won't be super important to what we talk about going forward. So I'm going to sort of like devoid myself of topological talk for the rest of the talk. So I finally get to define this a to the z thing instead of saying a to the z. This is actually so it's the set of all bi-infinite strings with symbols from our alphabet A, and it's called the full A shift, or the full shift on the alphabet A. And so so we can go ahead and take the shift map idea and we can go ahead and scale it up to 2 dimensions. So a shift map in 2 dimensions is a little bit more free. So instead of just moving left or right, we can go ahead and shift by any vector that can be formed with integer values. So as an example, if we look at a point in the full shift on the alphabet of A, B, C, and we shift by the vector 2 in the x direction, in the horizontal direction, and 1 in the vertical direction, you can see that that red block of A, B, C is moved over 2 and up 1. And so that's sort of how a shift map may work, or in this particular example of a shift map would work in 2 dimensions. And then a 2-dimensional shift space is going to be directly analogous from a 1-dimensional shift space. We're going to be shift invariant under the shift map for all vectors, all integer valued vectors shift maps. Well, let's say that one more time. So we're going to be shift invariant under all sigma sub v, where v is just some integer valued vector. And then 2, we're going to be closed with respect to the product topology on the full 2-dimensional A shift, which is that AZ squared thing. So we have shift spaces, and we can finally start talking about different types of shift spaces and their complexity. So the type of shift space that I'm going to focus on for this talk is going to be a shift of finite type. These are relatively more accessible, and it's because they're defined by having some finite forbidden words list. So a shift space X, which is equal to the restriction by F, which is why that X looks a little bit different. It's a different typesetting to X, is described by a finite forbidden words list, F, which is a subset of all of the finite words on the alphabet A. So this is the 1-dimensional case, right? And this is called a shift of finite type. So the main example that I will use to sort of talk about this and sort of give you some ideas for what this thing looks like is the golden mean shift, which is probably considered the most accessible non-trivial example of a shift space. So we're going to go ahead and consider the restriction by F, where the F is just 2 adjacent ones. And this is, so this, we'll see also briefly why this is called the golden mean shift. So some points in the space include these three, and the important thing to note here is that in none of those 3 points, at least within the range that we can see them, right, because these go off infinitely in both directions. I wouldn't be able to write out down the whole points, but at least based on what we can see of them right now, there's good evidence that they would, or like there is some evidence, maybe not good evidence, we don't know a lot of their values, right? There's evidence that these points would be in the golden mean shift because in none of them does the string 1, 1 appear. So as an example of a point that's not in the space, we could have some x that's equal to this 0, 0, 0, 1, 1, dot 0, 1, 0, 1, 0, 1, and continuing on in both directions, is not in the restriction by f because that string contains 2 adjacent ones, which I've gone ahead and highlighted in red. The golden mean shift is a thing, and we'll talk about its generalizations here in a second. But the so in 2 dimensions, in this so I guess we're gonna do that now. I wrote this talk, I should know what's going on. So the way to move that up into 2 dimensions is to start talking about a 2-dimensional shift to finite type, which instead of having a finite forbidden words list, is going to have a finite forbidden patterns list. So instead of x being equal to the restriction by f, where f is a set of finite forbidden words, f is going to be a set of finite forbidden patterns. And so there are a handful of ways to go ahead and generalize the golden mean shift and generalize that no adjacent 1, 1 condition. And I'm going to go through all 3 of them. The first one is what is usually called the 2-dimensional golden mean shift, which I'm going to shorten to the 2-GMS, the 2GMS. And that's equal to the restriction by f, where your forbidden patterns list is given by horizontal 1, 1 and vertical 1, 1. So I've gone ahead and given some examples of an example of a point, and then like a shift by that, a possible shift by that point. And the one thing to note is that where the ones are highlighted, right, there are no 2 adjacent ones and there are no vertical ones. So hopefully the red ones help you quickly see that the horizontal 1, 1 and the vertical 1, 1 pattern does not occur in either of those points. The second generalization is something that comes from chess. It's the non-attacking king's shift. So x is going to be equal to the restriction by f, which is given by the finite forbidden patterns list of horizontal 1, 1, vertical 1, 1, upper left, lower right diagonal 1, 1, and lower left, upper right diagonal 1, 1. And so this comes from chess, right? So the idea is if you're on a chessboard and you have 2 kings on the board, the only way for one person to, or for the game to never end is the kings just need, or for the game to be a draw is for the kings to be separated by more than 1 space, right? If the kings start next to each other, then whoever goes first can kill off the other king. But if they're separated by at least 1 space, because you can never put yourself in check, you either call the game a draw or the kings move around the board forever. The non-attacking king shift takes that idea and generalizes it up to however many players of chess that you want on the board at the same time on a board that is infinitely large. So go ahead and plop kings down on the board such that no 2 kings are adjacent with respect to how the king can move across the board, which is 8-directional movement, right? So that's why you have the addition of the upper left, lower right diagonal 1, 1 and the lower left, upper right diagonal 1, 1 in the finite forbidden patterns list. Again, you can sort of see how the ones are a little bit more sparse in these points, because once you have a 1, you can't have a 1 in any of the 8 spaces around it. And I've gone ahead and given examples in this case as well. And then the last possible way you could generalize the golden mean shift is something that's a little bit more obscure. It doesn't follow as naturally, right? So in the 2-dimensional golden mean shift, we had just a horizontal and vertical. So we had like a 4-directional a golden mean restriction. And then in the non-attacking king shift, we have an 8-directional golden mean restriction. But then this next one comes from more of the applied world. It's read-write isolated memory. And so read-write isolated memory is actually just any storage medium where you can not have two adjacent 1 bits next to each other. And you can't, I believe it's like you can't do a write process, more than one write process in the same run through your medium. Which I should probably be checked on. But that was a question I was asked when I gave this talk during the STaRS seminar that I did not have an answer to of where this applies. This is a scheme for data storage. So this is equal to the restriction by F, where our finite forbidden patterns list is horizontal 1, 1, and then upper left, lower right diagonal 1, 1, and then lower left, upper right diagonal 1, 1. And so the way that you could think of this as a golden mean shift generalization is that we're respecting all of the possible horizontal adjacencies, like in the one-dimensional case, but in the two-dimensional case, the vertical direction is new. And so in that respect, you could think of vertical 1, 1 as being free because it doesn't have any horizontal component to its adjacency. And so you can see in these examples of points in the read-write memory, the read-write isolated memory shift is a little bit different than non-attacking kings and the golden mean shift because you can have these lines of 1s throughout points in your space. Whew. Let's talk about, so we've got some examples of shift spaces in both the two-dimensional case and then one in the one-dimensional case, and we know sort of some examples of what these things look like and where they come up or where they're inspired from. So let's talk about their complexity. So the main question is to talk about complexity is, well, how many different finite configurations are allowed in a shift? How complicated can some finite window of your points be, or how different can they be? And how fast does that number grow as, if you're thinking in the context of data storage, the capacity of your system grows, or if you're just thinking mathematically, the length of your abstract word grows. So the answer to that question is usually thought of as entropy, and in the one-dimensional case, entropy is for a given shift space, the entropy of that space is given by this limit where that b sub n of x is going to be the set of all words of length n that can appear at some point in x. Now it's important to note that this limit always exists, and that has to do with the fact that the number of words in your b sub n of x set is bounded above by the size of your alphabet to the nth power. So you have a bound for every n on that set. And then also the other thing that's important is that this sequence of words in the one-dimensional case is subadditive, which means that if you have two words that live in your language for a shift space, there's always going to be some third word that you can shove in between them to make those two allowable words show up in a larger word. And so that sort of gives this sequence b sub n of x of any given shift space a sort of like Fibonacci-like recurrence. So it grows with at an exponential n rate or lower, but not higher than exponential n, because the highest it can grow is at the rate of the alphabet size to the nth power. So that was another question that I was asked, but I wasn't focused on the one-dimensional case, so I had not prepared an answer, and that was just awkward. So, when you're giving a talk, just make sure you know the simple things too, just so that you don't get stuck on something that you're not focused on in the talk. Notes to my future self. So entropy is great because under some notion of conjugacy invariance, there are these things called sliding block codes in symbolic dynamics that if you have a bijective sliding block code, that's an example of a conjugacy in the symbolic dynamical case for the shift spaces. And when you go ahead and map with those conjugacies, this value doesn't change, which is great, because then this thing classifies a complexity of a collection of systems and not just one system. And then 2, entropy is actually very easy to calculate for shifts of finite type. And there are some estimation techniques that you can make using shifts of finite type, which I think I've talked about on the channel at some point before, probably in that like really long live stream I did just to get comfortable doing like a Zoom lecture. So I'll put that up there as well. It's pretty long. I don't expect people to watch it, but like I left it up there because it was me talking about math. Anyway, so let's go ahead and look at an example of why it's easy to calculate in one dimension. In particular, there are a lot of combinatorial tools that are available in one dimension. So this is a sort of like a mass of different combinatorial things that you might want to use for the golden mean shift. So on the left, I've got a word building diagram, which is just a tree that where you go ahead through the tree by adding different symbols to build larger and larger words from other symbols. And what's really cool about the word building tree for the golden mean shift is that you get this sort of Fibonacci recurrence that occurs, right? So if you combine, if you add a 0 to both the red and the blue highlighted rectangles, you get the purple ones. And then if you add a 1 to the beginning of the dark red rectangles, you get the light red ones. And so that can be summarized in the Fibonacci recurrence of if you add the columns of the previous to the number of things in those columns, you'll get the number of things in the next column. So that's why I've got those circles up top with the Fibonacci numbers, because there's 1 thing in the first column, 2 things in the second column, and then 1 plus 2 equals 3 things in the third column, 2 plus 3 equals 5 things in the fourth column, and so forth. But the thing that I want to talk about more is the graph on the right. So what's really nice about having a finite forbidden patterns list is that the length of your words is that you can't hit is finite, and so you can go ahead and draw some directed graph, which is called an edge shift usually, if it's labeled in this way, where as you walk around the graph, if you go ahead and pick up the symbols that are labeled on each edge, you can go ahead and build all of the possible finite words that are allowed in your space. And if you go ahead and if you think about walking around the graph in 2 directions and going on forever, you actually can generate all of the points in your shift space as well. And so these directed graphs have an associated adjacency matrix, and there's a little bit of like matrix theory / Perrin-Frobenius theory in the background here, but it turns out for shifts of finite type that if you've got a type of matrix like this one that is, I believe it's like irreducible right resolving is the technical string of words for it, then the entropy value, that limit calculation, ends up being that this lambda AG, which is going to be the Perron eigenvalue, or for us, the most positive eigenvalue of that adjacency matrix. So for the golden mean shift, it turns out that the entropy of the golden mean shift is the log of the golden mean, which hence why it's called the golden mean shift. And so there's a whole, we could go down a rabbit hole there, but I want to go ahead and talk about, well, how does all of these combinatorial tools work in 2 dimensions? And so let's just think about it for a second. In 1 dimension, you've got these words of length n, and you're just trying to find some algorithmic way to add 1 more letter. And the directed graph lets us do that really quickly for shifts of finite type. But in 2 dimensions, you've got this n by n block of things, and so the analog is this n by n block of symbols, and you want to go ahead and add a row and a column to that to make the analogous n plus 1 by n plus 1 block. So you're going to add 2n plus 1 things to, oh no, did we Okay, 35 minutes in, and I thought it froze, and I'm, okay, that was... Anyway, so you're going to add 2n+1 things to your n by n block, right? And so there's a lot more things to take into account as you're trying to algorithmically build that up. So entropy in 2 dimensions is defined in a similar way to 1 dimension. I'm going to be careful here and say the limit supremum instead of just a limit, because in a few papers by Lind and a few other people, it comes up as both a lim sup and a limit. So I'm just staying on the safe side and using a lim sup. And the entropy given by a 2-dimensional shift space X, which is a subset of the 2-dimensional full shift, is going to be given by that lim sup of the number of n by n block, the log of the number of the n by n blocks in your space, all over n squared. And so the main question then, right, is, well, if we were able to do an example in 1 dimension, let's go ahead and do an example in 2 dimensions. How would you start? And the problem with that is that no one really knows how you would start. The question is open for what the entropy value is of the golden mean shift, or the 2-dimensional golden mean shift for all possible generalizations of the 2-dimensional golden mean shift. So read-write isolated memory, the non-attacking king shift, and the 2-dimensional golden mean shift, as it's traditionally referred to, all don't have a closed formula. And there are estimates out there, but no one knows what its exact value is. And also, like, part of the reason why it's a hard problem to figure out is that the machinery that you need to use is different. So Lind showed that there was the entropy of a shift of finite type is always one of those Perron eigenvalues. But Hochman and Meyerowitz in 2007 went ahead and showed that if your dimension is greater than or equal to 2, then the class of entropies on or of d-dimensional integer lattice shifts of finite type coincides with the class of right recursively enumerable non-negative real numbers, which is just a big long string of words that means that there are Turing machines or computers that have to approximate that entropy value from the right using rational numbers. This was actually a theorem that when we were working on the project back during my senior year of undergrad that we didn't really think too much about. We didn't stumble upon it. And so we probably would have went a different direction for what we did if we knew about this thing. But we didn't. And so we didn't go the Turing machine route. Instead, what we went ahead and did is started to trying to throw things at the wall to get a complexity value, and that's where this thing that we call the path entropy comes up. So the idea behind path entropy is to make the entropy calculation look more like the one-dimensional case. And so just as we go through pictures here, remember that you can associate tilings with symbolic dynamical systems. So if we've got some tiling or associated symbolic dynamical system, and we've got some path through that system, we want to know exactly how many choices we can make combinatorially on the red path. But then because we know that entropy is a hard thing to calculate, and being able to draw a path through the space and count everything on it it would be an equivalent problem to figuring out how to count all n by n blocks, we sort of lowered our expectations. And instead of wanting to be able to count exactly everything else, we just want to have lower and upper bounds that are reasonably bounded on the rest of the points, or in this case, on that blue path. So I need to define what a path is. So a path is going to be a directed graph, which is finite or infinite, satisfying the following properties. 1, each node of that path is going to be a subset of the integer lattice. So it's going to be some collection of symbols that lie in a particular shaped window. And it needs to be able to be covered by a collection of tiles or symbols, right? So your shift space needs to be able to realize a tiling or realize a point in the shift space, which is also a non-trivial problem. 2, each node has no more than one outgoing edge. So it's just it's a unary tree, the path that you follow doesn't branch off into multiple routes as you travel along it. And then lastly, all of the nodes along a path are all the same shape. So we want our counting to be relatively uniform. And we'll see that even with the same shaped nodes that the counting has a little bit of variability here in a second. But the main goal is just to have something that's computationally tractable, and having all the nodes in the path be the same shape helps us count things with less difficulty. So we're going to go ahead and call a primary path an infinite path with a number of allowable choices at each node can be determined exactly, and that's going to be given the previous nodes on the primary path are already chosen. And then the secondary path is going to be an infinite path that covers just the remaining symbols in the integer lattice or in the plane that have not yet been addressed by the primary path. So as we were throwing things against the wall, we were thinking about long tilings and ended up with a example of a shift space that focused on connecting a Wong tile with the color of its edges. And so we looked at this a particular set of Wong tiles with 6 colors, with 3 colors, but we focused on symbols and thinking of the symbols as the edges of those squares instead of the whole squares themselves. And the additional restriction that we had was that any 2 outer segments in a line of 3 collinearly aligned segments being the same color would be forbidden. So there are some examples of forbidden words. The other thing that we wanted to avoid is that because we were thinking about this as coming from a tiling, we didn't want any square breaking configurations to be allowed. So you couldn't have 4 vertical segments that are aligned in a square and don't form a square on the integer lattice. So, So that was the defining finite forbidden patterns list. It's quite a big set as compared to the gold mean shift. So that's why I've only given a handful of examples of what's forbidden. And so here's some examples of an allowed word. So if you look on the left, no 3 collinearly aligned segments are the same color, but notice that those the 3 vertical black lines in the first block of 3 squares is allowed because those are not collinearly aligned, right? They don't fall in a line. But then in the not allowed one, those 2 the vertical black red black symbol structures are forbidden by our forbidden condition and therefore would not be allowed. And so we went ahead and figured out a path for this thing. So we had a shape of a node, and the primary path is going to be 12 symbols. And so the way we denoted it is a blue square with this hashtag in it. So we're thinking about the lines that go out from the square, each of those 8 lines that go out from the square, and then the 4 interior edges as well. And then after we did that in the spiral pattern, the secondary node would be just those green squares that are left over after we choose everything on the primary path as we defined earlier. So the thing that's important to note is that we can actually choose everything on the primary path. So if you look at the center square, at that point in the primary path choosing process, nothing would have been chosen. So we can actually go ahead and have free choice on 8 of the things in our primary node, in that first primary node. And then the other 4 would determine a collinearly aligned segment of 3 colors. So you would only have 2 choices on the last 4. So if you think about choosing the bottom 2 and then the right 2 and then the interior 4, you would have freedom on all of those 8. But then when you chose the left exterior 2 and the upper exterior 2, then those would be where you would run into possible restrictions with the lower exterior 2 and the right exterior 2. So we have around 3 to the 8th times 2 to the 4th choices on a primary node. But that changes, right? So as you walk around the path, there will be places where the restrictions will interact with each other along the primary path, but it's okay because we can still count everything exactly. The lowest that it will get will be in the bottom, so in the bottom right, in between the rightmost one and the bottommost one. Along, there are squares like that one where you'll have 2 to the 8th times 3 to the 4th choices instead. And that happens asymptotically 1/4 of the time. So as an analogy to n by n blocks, we needed to go ahead and develop a concept of an entropic path of index big N, which we're going to call this E sub big N. And the idea of an entropic path is that we've got this primary path and the secondary path, and we're going to go ahead and walk along the primary path and count everything up to big N along the primary path. And then we're going to go ahead and come back around to everything that is completely determined, or that we have no freedom on in the secondary path that we can only just estimate, right? And there will be, so for in this example, the picture on the right is the entropic path of, it has the nodes labeled for the entropic path of big N equals 9, and so we go around 9 vertices on the primary path, which is shown in those, the 3 to the 8th, 2 to the 4th, and that thing on the right on top that's boxed in red, right? So we pick all the things on the primary path, and then we come back to the first node in the secondary path, which is going to be that one just above the center primary path node. And it turns out for the secondary path that we bound our choices between 1 and 2 to the 4th. So if we had 2 to the 4th everywhere, that would be a high estimate. If we had 1 everywhere, that would be a low estimate. And so the entropic path of big N equals 9 is actually going to have 13 vertices in this case. And we can't do anything more because once we try to pick another secondary path node, we'll have some complete freedom on the next possible node in the secondary path. So, as an analogy to the n by n blocks in the computation of two-dimensional entropy, we define the number of allowable ways to choose symbols on E sub big N as this F sub X of E sub N, which I don't exactly remember why we chose that set of symbols, but it's looking back, it's like kind of a gross way to denote something. So yeah. And that let us define what path entropy was. So for a shift space X and a given primary and secondary path pair P, which is equal to P1, where P1 is the primary path, and P2, where P2 is the secondary path, we define path entropy to be H sub P of X, which is equal to this limit as big N goes to infinity of the number of, the log of your F sub X of E sub N that we just defined on the last slide, over the size of this union over the vertices on the vertex set of the entropic path of length n. So the important thing to note is that the union is important because that's what gives us an analogy to the n by n blocks. So where we had n squared before, which would be the number of symbols in an n by n block, this union of the vertices, right, because those vertices are subsets of the integer lattice, that union counts how many symbols, symbol spaces that we've encountered along our walk along the integer lattice. Along our walk along the primary path and secondary path on the entropic path of big N. So again, in this formula that's kind of hefty, E sub n is the entropic path of index n, and V sub n is the vertex set of the entropic path of index big N. And so again, you can sort of see an analogy to the two-dimensional entropy. And so we had this new way of thinking about the complexity of a space, and we had all these questions, but the first thing we wanted to go ahead and do, because we were running out of time to work on this project, was to just see if it gave us some estimates. So for the Happy Robots shift, we got pretty okay bounds compared to some naive computations that we did that had a much wider spread, when we went ahead and assumed that everything on the secondary path was totally determined and only had one choice, we got around like 0.6 as our path entropy estimate value. And then on the higher end, when we assumed that we had 16 choices, or 2 to the fourth, 2 for each thing in the green box, we got around like 0.7577-ish. Right, and again, reminder here is that path entropy is something that we defined and is meant to be approximable, or meant to be like computationally economical enough that we can estimate the associated complexity value quickly. Right, so that's why we were happy about the spread being a little bit that's why we're happy about this spread of estimates, because a lot of the naive computations that we did that took a lot more work to do to like actually count out n by n blocks and like the golden mean shift or other things was for a particular n took a lot of time and didn't give us very strict bounds, or like the bounds that we got were way more spread out than the one here. So it was great. We were able to estimate something, and then the next thing to do was to test it against an example of a shift space where we knew the entropy. So there are a small handful of two-dimensional shifts of finite type where we actually know the entropy value. And some of these are computed in a measure theoretic way, and like 1 or 2 of them are computed via a combinatorial way. And since our path entropy thing was a combinatorial approximation, we wanted to go ahead and look at one of the combinatorial examples. And so a easy candidate that took us about a week to figure out was that of Ledrappier's example. So the counting method for Ledrappier's example is well known because, and I'll go through it here in a second, and it's an example of a shift of 0 entropy. So in a way, it's not super interesting in that it's not super complex. But the way that you go ahead and argue that Ledrappier's example has an entropy value of 0 is you go ahead and, first off, what is Ledrappier's example? It's this, it's the shift of finite type where the finite forbidden patterns list is you cannot have an even number of orange squares in your in right-facing L's of size 3. So the way to count this is and make the argument that Ledrappier's example has an entropy of 0 is to go ahead and just choose a row of symbols that are n long. In this case, we're doing 9 just because it'll fit on screen, but you could do this for any n. And if you go ahead and choose symbols in a row n long, you're never going to encounter an L-shaped window. So you haven't determined anything yet. And the next thing to do is to find somewhere close to the center, or pick any column. We'll pick something close to the center because it'll be important later. And just pick n-1 symbols down so that you get a row of length n and a column of length n that are chosen. Again, when you choose this column of length n, you haven't encountered any L-shaped windows, so nothing's restricted yet, and you have free choice on all of those 17 spaces in this case, or 2n-1 spaces in the case of n being a general value. But the cool thing is that once you do this, and you start looking at all of the L-shaped windows that could occur in this square that is n by n, you can actually determine everything. So if you start along, if you look at the L-shaped window that hugs the base of the T and where the stem of the T starts to file down, you can actually determine that square will be orange, right? And then you can go ahead and do that similarly throughout the rest of the entire square. And so that means that we only had free choice on 2n-1 spaces. And so the entropy calculation comes out to be this mess, which ends up being 0 because the growth rate of your words is only linear and not quadratic. Or the growth rate of your n by n blocks is linear and not quadratic. So let's go ahead and compare with a path. So the way we're going to do a path is we're going to just spiral out along a T. So that's going to be our primary path. And then once we spiral out or along a T, after we do that so many times, we're going to get some T that is a certain height. And we're going to go ahead and look at entropic paths of index n like that. In particular, we're going to go ahead and let K be the index that gives us an entropic path of length K that such that it gives a T of height little n. And so we know from earlier that once we have a T of height n, we can actually determine that whole n by n square. But in addition, we have a larger determined area. So we'll actually have this upper triangle thing and this lower triangle thing, a lower right triangle thing, to fill out where stuff is determined by our primary path. And so for these big K, we're going to have the same amount of freedom as we did in the case of entropy, and there are n squared symbols in the square, and there are two triangles of symbols out, one to the right of the square and one above the square, that are of height n minus 1. And so the number of things in our vertex set of the entropic path of index big K is going to be n squared plus 2 times the n minus 1th triangular number, which is a combinatorial thing. I recommend, if you don't know what that is, I recommend just giving a quick Google search, and you can sort of, there are n-gon numbers, and it's just based on how you can form triangles with points and things like that. That was a thing, and it was great because that let us go ahead and do an path entropy calculation for this thing, and we got that it's 0. Well, it's less than or equal to 0, but we also know that path entropy has to be greater than or equal to 0. So we figured out that the path entropy for this particular choice of primary and secondary path gave us 0, which is awesome because we were aligned with entropy for one of the known examples of entropy. But this just led to a lot of questions. Because we didn't have a ton of time to prove stuff about this new complexity measure, we just were able to do a few computations with it and get a feel for it. We knew that, well, as you're working with this primary and secondary path pair, when you look and try to compare to entropy, you've got these n by n blocks that occur within your points in space. And for some little n, you can sort of fit an entropic path inside of one of those things, but then as you go farther and farther out and increase the index of your entropic path, you're eventually going to cover that n by n block. And so in a way, we're doing a similar process of looking at larger and larger complexity, larger and larger patterns, and trying to gauge complexity by looking at larger and larger patterns. It's just that our patterns are a little bit more weird than just your basic n by n square. And so that begged the question of, well, is path entropy a conjugacy invariant? Is it somehow directly connected to the entropy calculation? Can you somehow do some sort of squeeze on the values of both path entropy and entropy to say that they're the same, that they may be the same value, or that they may be conjugacy invariant? Or rather, for conjugacy invariance, it's not that you squeeze them, but instead it's that if you map with a conjugacy, does there exist a primary secondary path pair that might be a direct result of that mapping? Like somehow the conjugacy might shift nodes around in the path or change the shape of the nodes in the path, but can you figure out, does path entropy stay constant along those sorts of transformations if you allow the paths to change along with the conjugacy? If you don't, then does it all, that would be a stronger statement, and does that hold is also another question. Also, like, when is it possible to find a good path? The happy robot shift that we worked with was something that we sort of cooked up to sort of make things work nice and be estimable. but we weren't able to necessarily find a great path for the golden mean shift. So what makes those two shifts different is another way of stating that question. And then lastly is, well, this sort of goes back to the conjugacy invariance thing. Is it possible to find two different paths that give different values for path entropy? This seems highly likely, just because there's so much freedom that you can have with moving a path around, right? Or how you move throughout the integer lattice and call it a path. But that was sort of like what we were thinking about near the end of the project, where we were running out of time and more focused on presenting sort of the expository dive that we did into symbolic dynamics to the rest of the seniors during our comprehensive project presentation, then actually working on developing new math. So that's it. Those are my references for this version of the talk. And yeah, it's this was an hour. So I'm gonna just sort of end it here. Thanks for watching if you decided to stick through this, and if you did, hopefully this was somewhat interesting or got you thinking about how people think about math, about certain things. But yeah, I don't have much to say in closing, but that was my talk that I gave as a part of the STaRS seminar at UNT about 2 weeks ago, or well, March 19th, 2021. And yeah, thanks for watching. I'll see ya when I do another update or another talk video.